So, hello everyone, and welcome to this talk related to Multipath TCP on smartphones. So, as you probably know, smartphones are popular devices that are multi-homed. It means that they can connect to both the cellular network and the Wi-Fi network. And today, there is something wrong with the classical TCP. Because when you have a TCP connection, you can stay fully on the Wi-Fi network, or you can stay fully on the cellular network, but you cannot use both networks on the same connection. So to fix this issue, Multipath TCP was created and allows to use several paths for a single connection. And these paths are called subflows. You can start a Multipath TCP connections like a classical TCP connection with a three-way handshake, so SYN, SYN, ACK. And you have that both hosts to be Multipath TCP capable to start a Multipath TCP connection. Then, once you started the Multipath TCP connections, you can create additional subflows in a four-way handshake, and then you can spread your packets over all established subflows. So, what do we know today in wireless networks? We know that Multipath TCP is able to aggregate the throughput of both networks. We also know that it has an handover capability to handover all your traffic from one network to another. It can also reduce the latency variations of bulk downloads. But what is, in fact, the performance of real smartphone usage on Multipath TCP? We have the Apple Siri. In fact, Siri uses Multipath TCP, but there is no public dataset and so no public measurements. And this talk fixed this issue. So we will first present our deployment architecture to make the measurements, then we present the characteristic of our datasets, then the interesting part, the results, and then we'll conclude. So about the deployment architecture, in fact, on the internet, very, very few servers are Multipath TCP capable. So if you want to enable Multipath TCP on smartphones, you have to put a proxy, a SOC proxy here, that is Multipath TCP capable, to enable the smartphone to use Multipath TCP. And then the SOC proxy can easily relay all the traffic to the actual servers. And the smartphone, of course, is configured to proxy everything on the SOC proxy. And this is also interesting since you can collect all packet traces at the proxy site. So about the characterization of our dataset, we distributed a dozen of Nexus 5 smartphones to users, and they say, okay, you can do anything you want with your smartphone. And typically, they installed actual Android applications like YouTube, Snapchat, and so on. And we collected around 25 gigabytes of data over approximately 400,000 of connections during a little less than 2 months. Our traces only consider IPv4 packets because ShadowSock does not support IPv6, in fact. And we figure that most of the connections are DNS, HTTP, or HTTPS. In DNS is because we run DNS over TCP. And we confirm also the tendency that smartphones are, of course, data consumers instead of data producers. So looking at the profile, the byte profile of the connections, we show here a cumulative distribution function over all the Multipath TCP connections, and we show the number of bytes that are carried on. A first thing to note is that nearly all bytes, in fact, are carried on HTTP or HTTPS connections. And we can have very heavy connections in terms of several megabytes, but in fact, most of these connections are less than 10 kilobytes. 85% of the connections have less than 10 kilobytes. And you observe also similar trends for the duration of the connections, where most of the connections last within seconds, whereas you can have several connections that last more than 1 day. So, about the interesting part, the results. To understand the behavior of Multipath TCP, we will answer the 5 following questions. And we will start with the first one, because since Multipath TCP is able to use multiple paths, we may ask, how many paths are created by a Multipath TCP connection? And let's introduce first a challenge that is introduced by Multipath TCP. Because you use multiple paths, you have to create your paths. And there is an algorithm in Multipath TCP which is dedicated to this, which is called the path manager, which will create actually the subflows. And the studied path manager is the default one in the default implementation is the full mesh path manager. It is the full mesh path manager on both the server and the smartphones. And it makes the client create subflows on all available network interfaces. Knowing this, when we count the number of created subflow per connection, we can have a lot of subflow on connection. The maximum that we observe is 42 subflows on a connection, of course not concurrent. But yeah, 2/3 of the connections actually use only one, create only one path. And no several ones. And in fact, there are several explanations to it. The first one is that, yeah, the connections, as we shown previously, are quite short for the majority of them. Also, you can have only one network interface. For instance, you can be out of any Wi-Fi access point reachability. Or the user can say, okay, I will turn off my cellular interface and only use the Wi-Fi. And if your connection is, again, quite short, it has no possibility to create multiple subflows. So the first thing to note is that, yeah, most connections, even on Multipath TCP, use only are single paths. Now that we have counted the number of subflows that are created, we can now ask, yeah, but when are they created? And there we show a cumulative distribution function of the additional subflows, and we show the time relative to the connections they belong to, from the beginning of the connection to see when they were created since the beginning of the connection. And you observe that, yes, most of the connections, again, most of the additional subflows are created within a second, which is quite expected since the full mesh path manager creates subflows as soon as possible on available interfaces. But you also know that you can have very, very late establishment of subflows. In fact, the latest one we found is 37 hours. And these very late establishments, in fact, suggest network handover, since you have moved from one place to another and you get a new network. So this is typically what explains these late establishments. So, okay, so since Multipath TCP can use several paths, we can look at the characteristic of the different paths to understand how they can be used. And so we will now show the second challenge introduced by Multipath TCP, which is, where should I send my packets? On which subflow, in fact? And this question is again answered by another algorithm called the scheduler. And the default scheduler studied in the server and the smartphone is called the default scheduler, which sends the next packet on the subflow, the available subflows, showing the lowest round trip time. Knowing this, we can be interested, okay, what are the difference of round trip time that we can see on connection? And this is the case here. So we show connections having at least 2 subflows established. And we show the difference of round trip time between the subflows having the highest round trip time and the subflow having the lowest round trip time. And we see that only 20% of these connections, in fact, experience round trip time differences of less than 10 milliseconds. And in fact, most of the connections, 60% of them, experience round trip time difference between 10 and 100 milliseconds. And even worse, we have a few percentage, 3–4% of the connections that in fact experience round trip time differences of more than 1 second on the same connection. So yeah, subflows can exhibit very different round trip time. And now that we have shown the scheduler and the round trip time characteristic, we can ask, yeah, but how the scheduler will react to this characteristic of subflows, and how will it spread the data over the created subflows. So to answer this quite difficult question, let's show the spectrum of the scalar dynamics where you want to send 4 packets on a multipath TCP connection that have 2 subflows, one on the Wi-Fi and one on the cellular. You can say, okay, I will send everything on the Wi-Fi. Or, on contrary, you can send everything on the cellular interface. Or, you can use a round-robin fashion starting from the cellular the subflow. Or you can use a more bursty style, but keeping still 2 packets on each subflow. And in fact, there are still 12 other combinations of packets. So, yeah, and this number of combinations grows exponentially with the number of packets you have to send. So, the idea here is to characterize, in fact, the frequency of subflow changes. And to do this, we'll introduce the notion of subflow blocks, which is in fact a set of packets that are sent consecutively on the same subflow. So if you take this example where the smartphone sends 6 packets on its whole lifetime, and in this situation, you can in fact focus on 4 subflow blocks, which are shown here. With this in mind, we have a quite easy way to show the frequency of subflow changes. And now we can compute it on all multipath TCP connections. And so we did this. So we consider only, again, connections having at least 2 subflows. And we show the cumulative distribution of these connections with the number of subflow blocks they have. And so if you are on the left part of the graph, you are more in a bursty style, whereas if you are on the right part of the graph, you are more in a round-robin style. And in fact, if you are at 1, so 10 to the power of O, in fact, you have only use one subflow. So, okay, here we have shown only connections carrying at least 1 megabyte. And you can see, okay, most of the connections use quite well subflows and change sometimes. But in fact, big connections are not the majority in the smartphone traffic. The majority of the connections here are in fact connections having less than 10 kilobytes of data. And if you consider them, we see here that more than 70% of these connections in fact only use one subflow. They do not change from subflow. This means that in fact, since they represent the majority also of the connections, most of the connections, even if they have more, 2 established subflow or more, in fact only use 1. So, and there are several causes that explain this. The first one is that, yeah, again, the connection can be so short that in fact, the time you have to establish your subflow, your additional subflows, the connection to the data transfer is already over, so there's no point. Or you can have subflows, for instance, established on the 2G, and so the round trip time is so bad that it will never be used. Or you can have also subflows that are backup subflows, which is a multipath TCP feature that says, okay, I don't want to send anything on this subflow unless you have lost all the other non-backup subflows. Okay, so, yeah, but finally one can ask, why using multipath TCP at the end? And maybe we can ask, maybe it's for its handover capability. And to concrete this example, to concrete this question, let's take this example where you are on smartphone and you are watching a video from YouTube. So again, you start from on the Wi-Fi subflow, and you have also established an additional subflow on the cellular one. But the Wi-Fi exhibits a significantly lower round trip time, and so you only use the Wi-Fi. And the application does not touch too much, so you can stay on Wi-Fi. So everything is going fine. And then after some time, yeah, you have to move, and you are out of the Wi-Fi reachability. And so you lose the Wi-Fi subflow. In classical TCP, what will happen, in fact, the connection is broken. But since you are on multipath TCP, you can hand over all your traffic on the cellular subflow, and your connections can still go on. And this particular example shows what we call a data handover. And a data handover is, in fact, a recovery of a failure subflow, in that case the Wi-Fi, by another one, in our case the cellular subflow. And we can detect them simply by relying on TCP header, so you can simply look at the sequence number, the time of the packets, and the acknowledgement number. And if we consider only connections using at least two subflows, of course, because if you have a data endover, you have to use two subflows, a quarter of these connections actually experience data endover, which may mean that probably the data endovers are the main selling point of Multipath TCP on smartphone. And so to conclude, we can say, okay, Multipath TCP works well on smartphones, and you don't have to change anything on your device in terms of applications. In fact, smartphone application does not really need to have bandwidth and aggregation, but they can benefit from the data endover capability when a user moves from one place to another one, and where the networks availability are different. And this, in fact, is already running today. Because, yeah, you have Siri of Apple, but you also have Korea Telecom from Samsung that in Korea enable the same deployment architecture than us to enable Multipath TCP on smartphones. And so, yeah, our packet traces are released, the tools are open source, and you can get all the methodology at this URL. So, thanks for your attention, and if you have any question, feel free to ask.
Yeah, thanks a lot for the nice talk. I really like Multipath TCP, so I'm wondering, can you elaborate a bit on the SOX proxy, and if this might influence your measurements compared to the traditional Multipath TCP server?
Yeah, indeed. So, in fact, when you start a connection from a SOX proxy, you have to first establish a connection to the SOX proxy. Then, so since in ACK. Then, when this is done, you have to send a small SOX command. Okay, to which real server do I want to connect? So I have to send a message with the IP address of the host I want to reach and the port, of course. You transmit it to the proxy, and then the proxy will open the connection on the other side, and then you can. And of course, yeah, this may introduce some delay. At the proxy to actual server side, this is quite a low delay, in fact, because it is quite connected on it is an OVH server, if you see what it is. And so the delay between the actual server and the OVH delay is quite low. Yeah. But yeah, of course, it introduces for it.
May I ask a follow-up question? One follow-up question. When you run it on the server, you might have features like TCP segmentation uploading, which might influence your block sizes. You have this metric of the subflow blocks.
Yeah.
So how does this behave with your SOX proxy? Would you also see these, let's say, burstiness of the TCP segmentation uploading?
I must say that we don't have explored the TCP segmentation uploading, but yeah, it could be interesting to have a look at. But yeah, we didn't explore it.
Thanks a lot.
We have some time for more questions. Yes, please.
Did you not see any kind of problems with middle boxes that handle that cut off the detect that you are going to multi-sessions of TCP and cut off the sessions?
Yeah, in fact, it's a very interesting question. What we can say, on the Wi-Fi network, we didn't see anything going wrong. And on the cellular network, at the beginning, we had cooperation from the cellular provider to say, okay, no middle boxes. And so everything is going fine. And then we had to stop our measurement study because our cellular provider, in fact, they added some middle boxes that prevented multipath TCP connections. And so it falls back to TCP, yeah.
So did you encrypt your sessions from your smartphone to the...
Yeah, in fact, when you use SOCKS, you have to encrypt in some way, yeah, the data, but we use the lowest encryption scheme, which is a table on Shadow SOCKS, and it's simply a shift of bits which can be easily done, and the overhead should be very low, in fact.
Some more questions?
Nice. So your flow scheduler actually, it resembles a bit an SDN controller, you know? Because it needs to have some knowledge of the topology if you really want to schedule flows and buffers traffic properly.
Yeah, in fact, this is a main problem of today's scheduler, is that when you schedule your data, you have only a local view. So you have the view of the client, or you have the view of the server. And let's take, for example, the case where you have the smartphone that lose the Wi-Fi reachability area. So the smartphone knows it, but the server is not aware of it. And so, yeah, ideally, we should give more, and this is a future work, of course, is to give more view of the networks to the local participants. Yeah, of course.
Yes, and maybe another question?
So did I understand your setup correctly that you need this Shadow SOCKS client running on the mobile device?
Yeah, yeah, because we have to relay the traffic, of course.
So all decisions are made by this clients, so how new subflows being established. Did you compare your findings with the scheduling and managing implementation? You have this scheduling strategy.
Yeah, okay.
And you, since it is open source, you can check this allocation strategy in the source code. So
yeah.
Did you compare your findings to the allocation strategy used by the proxy client?
Don't see why the proxy clients will change
basically you know, you a priori know which strategy this client uses to allocate new subflows.
So in fact, what is going is you create when you create in fact two subflows from the client to the Shadow SOCKS client, because it is on the loopback interface first. Here you have two different subflows already, but not sure I'm fully understanding your question.
Are the applications on the mobile phone multipath enabled, or is this multipath only between the Shadow SOCKS client and the Shadow SOCKS
yeah,
server?
It's between the Shadow SOCKS client and the Shadow SOCKS server.
So all decisions are made by the Shadow SOCKS client on the mobile phone.
When the client sends a packet, it's the scheduler at the client that sends the packet, okay. But if the server is sending packets, and in fact this is most of the time because smartphone mostly consume data, when you watch a video, in fact it is the server, so the proxy at the server side that will decide, yeah, on which subflow will I send the packet. And yeah, of course, and there is some work to do there to give probably more view to the server to send maybe the packet where the client wants.
How does the server find this decision which transport channel to use? How does the server decide if it uses mobile or wireless?
Round trip time based, but it has no information about the actual interface it uses behind, in fact. So, no. In fact, the server cannot know like this if the subflow is in fact on the cellular or is on the Wi-Fi.
But it has to find a decision. So it has multiple subflows, and so it has to find a decision which subflow it takes to send the data to the mobile device.
should, yeah.
I would like to suggest, I mean, all these are interesting questions, and I know that there are a few more people that you want to ask. So let's, in order to keep the time schedule, I would suggest to continue the questions during the coffee break and lunch break. And let's thank again the speaker for this